There is a planet at the edge of our solar system that took humanity nearly 200 years to visit even once. A place so remote, so cold, and so shrouded in distance that for most of human history, it existed only as a number on a page, a mathematical ghost conjured by equations before anyone had ever seen it. And yet, when we finally did catch a glimpse of it, we discovered something extraordinary. Not a silent, frozen rock drifting alone in the dark, but a living, breathing, violent world, one of the most active and dynamic planets in the entire solar system. This is Neptune, the 8th planet, the last planet, and arguably the most mysterious world in our cosmic neighborhood. Today, we are going to explore everything we know about the ice giant at the edge of everything, where it came from, what it looks like, why its weather makes Jupiter's storms look almost tame, and what its moons might be hiding beneath their frozen shells. Because Neptune has a story to tell, and we have barely scratched the surface. Let us start with the discovery itself, because it is unlike any other in the history of planetary science. Every other planet in our solar system was found the same way. You look up, you notice a point of light that moves differently to the stars. You study it, and eventually you understand that you are looking at a world. Simple, visual, instinctual. Neptune was different. Neptune was found on paper first. In the 1840s, astronomers had been carefully tracking the path of Uranus through the sky, comparing its movement against what Newtonian physics predicted it should be doing. And something did not add up. Uranus was drifting slightly off course, pulled by some invisible influence. A French mathematician named Urbain Le Verrier looked at the problem, sat down with his calculations, and concluded that there must be an unseen body out beyond Uranus, a massive planet, exerting just enough gravitational pull to nudge Uranus out of its expected trajectory. He even predicted precisely where this unknown planet would be sitting in the night sky. When German astronomer Johann Galle pointed a telescope at that exact position on the 23rd of September, 1846, he found Neptune within an hour. A planet had been calculated into existence. Nothing quite like it had ever happened before, and nothing quite like it has happened since. But discovery was only the beginning of the difficulty, because getting any meaningful information about Neptune turned out to be a challenge of almost impossible proportions. At its average distance, Neptune sits roughly 4.5 billion kilometers from the Sun. That is 30 astronomical units, 30 times the distance between Earth and the Sun. When you try to observe Neptune from the ground, even through powerful telescopes, you are staring at a tiny blue smudge. Its detail is almost entirely hidden by distance. And the idea of sending a spacecraft out to investigate was not straightforward either. At current technological speeds, a probe needs somewhere in the region of 12 to 13 years just to make the journey. There was, however, a narrow window of opportunity. Once every 175 years, the outer planets align in a configuration that allows a spacecraft to use each planet's gravity to slingshot itself toward the next one, dramatically reducing the travel time. That alignment happened in the 1970s and 1980s. NASA, recognizing a once-in-several-lifetimes opportunity, launched Voyager 2 in 1977. After visiting Jupiter, Saturn, and Uranus, Voyager 2 finally arrived at Neptune on the 25th of August, 1989. It passed within 5,000 kilometers of the planet's North Pole, closer than any flyby of any planet during the entire mission. And for a few extraordinary days, the data came pouring in. Rings were confirmed, new moons were discovered, and for the first time in human history, we had a clear picture of what the 8th planet actually looked like. That single encounter remains to this day the only close-up study of Neptune we have ever conducted. Everything else we know has come from telescopes, primarily the Hubble Space Telescope, and, more recently, the James Webb Space Telescope. So what did we find? What does Neptune actually look like up close? The first thing you would notice is the color. Neptune is a deep, vivid blue, richer and more saturated than Uranus, which sits at a similar distance from the Sun. The difference comes down to methane. Neptune's atmosphere is made up of approximately 80% hydrogen, with helium making up most of the remainder. But it is the methane, sitting at around 1 to 2% of the atmosphere, that gives the planet its striking appearance. Methane absorbs the red wavelengths of incoming sunlight and scatters blue light back outward. The result is a planet that glows like a deep ocean. But the atmosphere is not simply sitting still. It is one of the most violent environments in the known solar system. Voyager 2 measured wind speeds in Neptune's atmosphere that stunned the scientists receiving the data. At the equator, winds were blowing at roughly 2,100 kilometers per hour, nearly the speed of sound. These are the strongest winds ever recorded on any planet. And what makes them stranger still is that the majority of these winds travel in the opposite direction to the planet's own rotation. Neptune spins one way, and its atmosphere tears across it in the other direction. The reasons for this are still not fully understood. During its flyby, Voyager 2 also spotted something else. A massive, dark, oval-shaped storm spinning counterclockwise through Neptune's southern hemisphere. It was quickly named the Great Dark Spot, and it was roughly the size of Earth. Winds along its edges were measured at up to 2,400 kilometers per hour. NASA scientist Heidi Hammel, who was part of the Voyager imaging team, later described it as one of the most dramatic weather systems ever observed anywhere in the solar system. When the Hubble Space Telescope was turned toward Neptune several years later, in 1994, the Great Dark Spot was gone, completely. No trace remained. Where Jupiter's Great Red Spot has been raging for at least several centuries, Neptune storms appear and vanish on timescales of years rather than centuries. Hubble has since observed a succession of dark vortices appearing, wandering across the planet and fading away. The most recent large storm appeared in 2018 and has been tracked ever since, slowly shrinking as it drifts toward Neptune's equator. The mechanics behind these storms are thought to involve bands in the atmosphere traveling at different speeds. Where two bands meet, the friction between them can seed a vortex. That vortex can sustain itself for years, as long as it remains within the right atmospheric band. But once it migrates out of that region and loses its energy source, it dissipates. The process is elegant in its logic, but the scale of it, storms the size of entire planets lasting years before collapsing, is humbling. But here is where Neptune presents one of its most intriguing puzzles. You might reasonably assume that Neptune, being the furthest planet from the Sun and therefore receiving the least solar energy, would be the coldest planet in the solar system. It is not. That distinction belongs to Uranus, despite Uranus being significantly closer to the Sun. Neptune radiates considerably more heat into space than it receives from the Sun. Something inside the planet is generating additional energy. The most widely accepted explanation is that Neptune still retains significant heat from the period of its formation. Primordial warmth left over from the violent collisions and compressions that built the planet billions of years ago, slowly leaking outward through the planet's layers. Uranus, by contrast, radiates almost no excess heat. One leading theory holds that Uranus was struck by a large object early in the solar system's history, something Earth-sized perhaps, an impact so catastrophic that it both knocked the planet onto its extreme axial tilt and disrupted the heat flowing from its core. Uranus has been slowly cooling ever since. Neptune was not hit in the same way, or perhaps not as severely, and so its internal warmth survived. That internal heat is now thought to be a significant driver of Neptune's extreme weather. More energy rising from below, more convection, more turbulence in the atmosphere above. The Sun is barely a factor this far out. Neptune receives roughly 1,000 times less sunlight than Earth does. The engine driving its storms is not above it, but beneath it. Deep inside Neptune, the structure grows stranger still. Beneath the atmosphere lies a mantle of water, methane, and ammonia, not in solid or gaseous form, but compressed into what is known as a supersonic or ionic state, conducting heat and electricity in ways that do not neatly fit our everyday categories of matter. This layer is sometimes called a water-ammonia ocean, though that description only captures part of its bizarre character. Even deeper, where the mantle meets the core, conditions become extraordinary. The pressure at Neptune's core is estimated to be around 7 million times the atmospheric pressure at Earth's surface. Under these conditions, the carbon in methane molecules is theorized to break free and, compressed by that unimaginable force, crystallize into diamond. Not diamonds as we might picture them, but perhaps a fluid layer of liquid carbon with solid diamond structures floating within it, and a constant rain of diamond crystals falling through the mantle toward the core. Laboratory experiments in recent years have begun to confirm that this process is physically possible. Neptune may contain more diamonds by mass than any other place in the solar system. Neptune also has rings. They were suspected before Voyager 2's arrival, but could not be confirmed from Earth-based observation. The flyby settled the question definitively. Neptune has at least 5 distinct rings, all named after figures connected to the planet's discovery. The innermost is the Gale ring, faint and broad. Moving outward, the Leverrier ring is brighter but narrower. The Lassell ring and the Arago ring sit between that and the outermost Adams ring, which is the most studied of the 5. The Adams ring has a particularly unusual feature. Rather than being uniformly distributed around the planet, its material clumps into several bright arcs, sections of the ring that are noticeably denser than the rest. These arcs have persisted since their discovery and are thought to be stabilized by gravitational interactions with Neptune's small inner moon Galatea, which orbits just inside the ring. But the precise mechanism is still not entirely clear. Most ring systems spread their material evenly over time. Whatever is holding these arcs together is still a subject of active research. And then there are the moons. Neptune has 14 known moons, all named after figures from ancient Greek mythology associated with water and the sea. Most of them are small, irregularly shaped, and captured objects, bodies that formed elsewhere in the outer solar system and were pulled into Neptune's orbit by its gravity. The outermost moons, Neso and Sao, orbit so far from the planet that a single orbit takes more than 25 years to complete. But no discussion of Neptune's moon system is complete without Triton. Triton is unlike any other large moon in the solar system. Begin with its orbit. Every other significant moon in our solar system orbits in the same direction as the rotation of its parent planet. Triton orbits backward, retrograde, and at a sharp angle of roughly 130 degrees to Neptune's equatorial plane. This orbital configuration is not something that happens to moons that formed alongside their planet. It is the signature of a captured object. The leading theory is that Triton was once a dwarf planet in the Kuiper belt, a distant, icy world orbiting the Sun independently, until a gravitational encounter with Neptune destabilized its trajectory. One possible mechanism involves Triton originally being part of a binary system, paired with a smaller companion. As Neptune's gravity pulled the pair apart, the companion was flung away, while Triton lost enough momentum to be drawn into orbit. Over billions of years, gravitational friction has since circularized that orbit, until it is now almost perfectly round, even while remaining retrograde. The consequence of this retrograde orbit is gradual. Triton is slowly spiraling inward. In approximately 3.6 billion years, it will cross what is known as the Roche limit, the boundary inside which tidal forces overwhelm the structural integrity of a body. Triton will be torn apart, and Neptune will gain a spectacular new ring system, potentially rivaling Saturn's in scale and density. But Triton is not simply a passive object falling slowly toward its end. It is an active world. Its surface is one of the coldest places ever measured in the solar system, around -235 degrees Celsius. Beneath a thin atmosphere composed mainly of nitrogen, the surface is covered in nitrogen and methane ices. And yet, Voyager 2 observed plumes, geysers erupting from the surface and reaching heights of 8 kilometers, before the thin wind carried their dark deposits hundreds of kilometers downwind. These plumes are thought to be driven by a solid greenhouse effect. Sunlight, even this dim and distant, passes through the transparent surface ice and is absorbed by the darker organic material beneath. The heat builds until a pocket of sublimating gas ruptures through the surface in a dark, streaking plume. It is one of the most alien forms of geological activity ever observed. And beneath the surface, there may be more. Triton's density and its rocky, metallic interior suggest that radioactive decay from its core could be generating enough heat to sustain a liquid water ocean between the rock and the ice shell above it. If that subsurface ocean exists, Triton joins Europa, Enceladus, and Titan as a world with the potential conditions for life as we understand it. The James Webb Space Telescope has recently opened a new chapter in our understanding of Neptune. In March of 2025, Webb released images of Neptune's auroras, faint but unmistakable ribbons of light shimmering across the planet's mid-latitudes. These are not the polar auroras we are familiar with on Earth. Neptune's magnetic field is tilted 47 degrees relative to its rotational axis, meaning that auroral activity does not concentrate at the poles in the same way. Webb's near-infrared instruments were sensitive enough to capture what no previous observatory had managed to see directly. At the same time, Webb recorded a dramatic drop in temperature in Neptune's upper atmosphere compared to Voyager 2's readings from 1989. The thermosphere appeared to have cooled by hundreds of degrees in the intervening decades, nearly half its former temperature. The reasons for this are not yet understood. Whether it is driven by long-term seasonal cycles, changes in internal activity, or something else entirely, the data opens far more questions than it answers. And that, in many ways, is Neptune's defining characteristic. For every piece of information we gather, the planet seems to offer 3 new mysteries in return. We have seen it up close exactly once, briefly, from a single angle, at a single moment in time. Everything else has come to us secondhand, through the filters of telescopes and the patient analysis of faint signals. We know Neptune has storms that dwarf our entire world and then quietly vanish. We know it hides diamonds in its depths and may shelter life-bearing oceans in the moons it captured. We know its outermost moon is slowly falling toward a catastrophic end that will reshape the entire system billions of years from now. There are currently no confirmed missions to return to Neptune. NASA's budget constraints have made the outer solar system a lower priority, and the window for another efficient gravity assist trajectory has long since closed. China has proposed a Neptunian mission with a potential launch window around 2033, which would represent a major step forward if it proceeds. But for now, Neptune remains largely in the dark. That feels significant somehow. We live in an age where we have mapped the surface of Mars in extraordinary detail, where we have touched the outer edges of the solar system with our spacecraft, where telescopes can peer at galaxies billions of light years away, and yet the last planet in our own neighborhood remains almost entirely unknown. Neptune does not make itself easy to reach. It sits at the edge of everything we consider nearby, vast and cold and ancient, radiating heat from its formation long before life appeared on Earth. It holds storms, diamonds, captured worlds, and frozen moons with buried oceans, all in a system we have glanced at once and never returned to. Perhaps that is what makes it so extraordinary. In a universe we are constantly being told we are beginning to understand, Neptune quietly insists that we have only just begun. Thanks for watching. If you want to keep exploring the most extreme and overlooked places in the cosmos, make sure you are subscribed and hit the notification bell so you never miss a new video. We will see you in the next one.